Hey, in the second episode, we're going to be looking at series circuits in a little more detail. Quick review, we can see this is a series circuit because there's only one path for current to flow through this circuit. If we disregard the leads of the voltmeter, there's only one path where current can flow. We can see that the value of current is the same as measured by these two ammeters everywhere in the circuit. A couple of things about Circuit Lab. So one of the things you might wonder is this number, this V3 SW2. These are just names which can be modified. So I can't have the same name twice on the switch. I can't have another place where I have a name of SW2. I can name this anything that I want to name it. See if I can learn to spell switch. I can put it there. Same thing for this ammeter. I could say that this is a Fluke 88, and we'll put that in there, and it's able to do that as long as I don't have that used anywhere. Also with our ammeters, if you want the current to read positive, if I were to insert it the other direction, we can see it's going to show a negative current just like a real voltmeter would or ammeter would do. Same thing for our voltmeters. If I were to take this voltmeter and flip it the other way, sometimes you might connect your plus and minus red and black leads backwards. That's what you'll have. So let's go ahead and put everything back up where I wanted it. Whoops, wrong place. Flip vertical, there we go. And let's flip this guy back to horizontal, there we go. So we're back where we were. We have 1 amp of current because the switch is closed. We have, the reason that it is 1 amp is because I have 2 volts. And 2 volts with 2 ohms ends up with Ohm's law. As this is solved, it tells us that that current is going to be 1 amp. If I were to change this resistance, if I increase the resistance, as we talked about before, if I were to take it and increase it, we can see that the current decreases. If I were to decrease the resistance below that value that we had it originally, we can see that that increases the current. So we'll go ahead and put it back where we had it, which was 2 ohms. That gives us 1 amp. Okay, if I zoom out, I can show you that I've got a couple of another circuit that's here. And this one is also a series circuit. We can see the series circuit. Here's our voltage supply, 2 volts, same as the other circuit. We have an ammeter here, which is showing 1 amp of current flow because the switch is closed, and we have a path for current, a complete path for current to flow through. And that one single path, disregarding the parallel connected voltmeters, of course, there's only one path for current flow through this circuit. All of the current must flow through this ammeter. Of course, the switch must flow through this R5 resistor number 5, flow through this ammeter, flow through this resistor, this ammeter, and back to ground. And we can see that if we look at those values of current, they're the same in both of these circuits. So this is 1 amp and this is also 1 amp. I have 2 volts as the supply and I have 2 ohms of resistance. In this circuit, I've taken that 2 ohms of resistance, if you would, and I've split it in half. So I took that resistor, I broke it in half, and now I have 2 separate resistors, which are each 1 ohms. If I put those back in the circuit, it's going to show, or in this circuit, it's going to show, both circuits are going to show the same thing. We can see, though, that one of the things that's a little different here is because I have now 2 resistances which are connected in series, I have 2 different voltage drops. And so here's one of the next rules that we're going to have on, or laws, whatever we want to call them, on series circuit, and that is when I have this series circuit, the sum, where I take addition, of the voltage drops, so what I measure across each of the components in a series circuit must equal the supply voltage. So I can see I have 1 volt here, I have 1 volt here. If I take those 2 voltage values, add them together, it gives me 2 volts. If I went out and borrowed everybody's voltmeter and ammeter in the shop and built this circuit, we can see that I've got 2 volts now dropped across these 2 resistors together. So if this kind of proves the point, or this rule, if I take this voltage and I add it to this voltage, I end up with this voltage, which is the same as the supply voltage. So the next rule that we'll talk about is that the amplitude, or the value of voltage that's dropped across a resistance, what I would measure with a voltmeter, is directly proportional to the value of resistance. So once again, what's that mean? Directly proportional. That means as I increase the resistance, if I increased one of these resistors, and let's change this from 1 ohm to a value of 3 ohms. And when I do, that increases the value of voltage that is dropped across this resistor. But our first rule the first rule we discussed today still stands. If I add this voltmeter with this voltmeter, I get the value of this voltmeter that's displayed on this one, which is the same as this value. So if I take this value of resistance, let's go ahead and we'll set this one to 3 ohms as well. And we change it to 3 ohms. Now they both have the same voltage dropped across them. This voltmeter has stayed the same the entire time, and it's going to stay the same no matter what I put in here. So let's set this to 120 ohms. This is still 2 volts. If I look at this, I don't have nice even round values now, but I have about almost all of the voltage, a very high percentage of it, dropped across this resistor, with the remainder being dropped across this resistor. So this is, if I look at this as a hydraulic analogy, let's go ahead and drop this back down to where we have 2 of these. So that we'll say that this is a hydraulic filter and that this is some hydraulic component which are operating. And here's our hydraulic pump, and we have the valve closed. We can see with our flow meter that we have 1 amp of current flow. We'll say 1 amp of hydraulic flow, or 1 gallon per minute, or whatever units you're using for hydraulic flow. As I start getting dirt in the system and I start filling this filter up, we can see that I end up with a restriction across this filter. And if you have a gauge across your pressure, or if you put a gauge across a filter, you can see if the filter is restricted as long as you're using the circuit, right, or you're using the system. Well, we can see in this case, what that's done is I can't do as much work as I could do before, because I've decreased the amount of electrical pressure. I've decreased the amount of pressure that I'm making available for this device, whatever it is, a cylinder or something, because I've dropped too much of my pressure across my filter. And of course, that reduces the hydraulic flow. So if I were to try to analyze or to troubleshoot this as a hydraulic circuit, I would have my flow meter in place, or I would put my pressure gauge across the filter, and I would see that's like, oh, this filter is restricted. Therefore, I need to go back. I need to change this filter, and let's put it back where it was. And there we go. Now we're back up, and everything's working as it should. So those are the 2 rules of series circuits. The sum of the voltage drops, when I take this voltmeter, the value of it, add it to this voltmeter, it must equal whatever the supply voltage is. So let's look at how I could actually troubleshoot that. I'm going to pause this and I'm going to change something in this circuit. We'll see if we can figure out what is actually wrong. We're going to try to troubleshoot it. Okay, so we can see now we still have 2 volts of the battery is still at 2 volts. So if we have a 2 volt battery, that's fine. We can see that we still have 2 volts. So if we were to take our, let's get a multimeter, and we'll drag a multimeter around this, or voltmeter, and let's see what we have for voltage. So if I were to get a voltmeter, let's go ahead and get one, and I put it across this guy, and I go ahead and I check my battery voltage, right? Because that's what I got to use. And we can see that it's supposed to be 2 volts, and indeed it's 2 volts. So that's not my problem, is it? It's not a problem of voltage. So my complaint is I've got whatever it is. If these were some light or something else, typically wouldn't be connected in series, but we'll say that these are lights, and that these lights don't work or are extremely dim. I can look at this and know by my voltmeter over here, if I look at what's dropped across this resistance, this light bulb, I can see that I have 1.996 millivolts. Well, what that means is if I look at that on my meter, that's going to be 0.001996 volts. That's really a low value of voltage. I've got 2 volts over here. This one shows the same value. If I borrow somebody else's meter, or I take my meter and I move it down here, I can see this. I can see if I put an ammeter in series with the circuit, it's like, well, this should be a lot higher current than that. I can go try it on another machine, and I can see that, you know, it's got 1 amp of current flow, and I only have 0.001996 amps. So really small amount of current. The other that really gives it away is I've only got 3.992 millivolts, so 0.003992 volts displayed on my Fluke 88. It should be 2 volts. I know that this is a series circuit and that I should have 2 volts dropped here. So if I were to get another voltmeter, or I take one of my voltmeters, and let's drag it up here and let's put it in the way that we would normally do it, right? Let's do counterclockwise. And I were to put this voltmeter across the switch. So the switch is supposedly closed, and supposedly we would expect almost no voltage to be dropped across a closed switch, because the resistance of a closed switch is supposed to be close to 0. We want it at a very low value. And we can see here that dropped across my closed switch, that has a value of 1.996 volts. Well, I bet if I take 1.996 volts and add it to 3.992 volts, that's going to equal 2 volts. I can almost guarantee it. And if we take our voltmeter lead, let's just prove that. Well, let's don't do that. If we take this lead and we were to drag it down here, put it down here at the ground, we can see that sure enough, it reads 2 volts. So if I check from this side of the switch to ground, I can see that I have a value of 2 volts now. So if I put it back up here where it was before, oh, Circuit Lab, don't do this to me. One of the great things about it, all right, let's drag this again. And there we go. We can see that now I have this back at 1.996. We shouldn't be reading that. If I were to take this switch, and I will go ahead and we'll give it away what's wrong here. If I were to open this switch, we can see that an open switch, because it has all of the resistance, and we look at our rule where the amplitude of the voltage drop across resistance is directly proportional to the value of resistance. Well, this is an infinitely, because an open circuit is basically an infinitely high resistance, it's going to get all of the voltage dropped across it. So if I look at these others, we can see right now some of these are showing something called nanovolts, and that's because I do have some resistance of this meter. That's something we'll talk about in another episode. This is some of the things that will cause you problems in troubleshooting if you get too carried away with this and say, well, this should be 0 because the switch is open. It's because I have an or a voltmeter connected. We'll go ahead and disconnect it, and we'll see that nanovolts. Nano has got nanopico. It's 9 zeros in front of it, so it's a really, really small value. We can see. I'll go ahead and put my resistance back. This is what we expect across an open switch. Across a closed switch, we expect a value to be near 0. And I'll go ahead and I'll fix this. It's real easy to fix these virtual circuits. We're going to set so that our resistance on has a value of 0. So there, I fixed the switch. I replaced it. We can see, as we expect, across a closed switch, we're going to have a value that is nearly 0 or is 0. In a real switch, we do have some resistance, so I'm going to put we'll put a little bit of restriction across it, and we can see that we have 10 microvolts. That's 10 millionths of a volt. So this is a really good switch if it has that little bit of a resistance. In real life, with your real meter, you will measure some resistance or some voltage across a closed switch. And your open switch, when it is open, you will cause some current to flow through through the meter itself, and that's stuff that we'll look at. These are the kind of things that I know that experience shows that it deceives a lot of technicians, and it makes it really hard to understand electricity. It's because we're looking at something called the real versus what the ideal is. And of course, in this program, I can set everything so that it's ideal, so that everything's nice and clean and pretty and has wires that have actual 0 ohms of resistance, where real wires definitely don't.